right? So I might have painted quite a bleak picture about epilepsy as disease, right? So I've said that even some of these most cherished ideas about the causes of epilepsy, that it's caused by hypersynchrony in neural firing, that this turns out not to be true. I've said that the idea that it's just caused by not enough inhibition or too much excitation, that there's no real evidence to support that. Um, so you may think that because of this is a sort of an untreatable disease, but in fact, the opposite is true. This is for a neurological disorder, this is a very well treated disease. Nearly all of the drugs, with a few exceptions, that target that treat epilepsy target the voltage-gated sodium channel. So let's have a wee reminder of the voltage-gated sodium channel, right? This channel that mediates the depolarizing phase of the action potential. When we have a cell that's sitting at rest, the activation gate of the channel is closed and the inactivation gate is open. Then when the channel is depolarized, it very rapidly opens, which is to say the activation gate opens, and that allows sodium to rush in. But then as the cell is held at that depolarized potential, then the inactivation gate closes. And when the inactivation gate closes, the ion channel is no longer conductive, and so then the channel goes back when the cell is brought back to a resting membrane potential, then that inactivation gate can open, can sort of get out of the way, and the cycle is ready to begin again. Okay, and we know that when we want to probe the function of voltage-gated sodium channels, we love to use voltage clamp. And so, we've seen protocols like this where we hold a cell at -70, step it down to -120 to remove any inactivation, to allow that inactivation gate to be completely open. And then we depolarize the cell to various test pulses, which causes the voltage-gated sodium channel to open, and we get a curve like this. And of course, it starts opening more and more, we get more and more current. Then the current starts to get smaller as we move towards the equilibrium potential. But if we plotted that as a conductance rather than a current, we would just see a sort of a sigmoid shaped curve of the ion channel being completely open by the time we reach about 0 millivolts. So another protocol we can run is this time dependence of the recovery from inactivation. So we know that if we do a big depolarizing step, so to -10 for 25 milliseconds, we get a nice sodium current. And then the sodium current goes away because of that inactivation. And then if we wait, 100 milliseconds or so and evoke another sodium current, well, it's just the same size, because while the channel completely inactivated, as soon as we bring the cell back down to -80, -90, -100, something like that, that inactivation gate opens again, ready for the next cycle. But as we move these two pulses closer and closer together, we see the second uh, lot of current that comes through the sodium channel gets smaller and smaller. So here we have only 3.4 milliseconds between the first pulse and the next pulse, one depolarizing pulse and the next polarizing pulse, and you can see that the channel hardly opens at all. So this is what that curve would look like of the ratio of the second pulse to the first. And you can see that basically the ion channel needs about 100 milliseconds to fully recover, and it sort of half recovers in about 25 milliseconds. These, yeah. Now, this is the important bit, that when you apply a anti-epileptic drug, for instance, this one, carbamazepine, CBZ, which is a very old anti-epileptic, something different happens. So here we see a train um, of currents being induced through the voltage-gated sodium channel. So they're just stepping it from -120 to 10, waiting 20 milliseconds in this case. And you can see that in the control condition, you do have the inactivation hasn't completely recovered, right? So the cell tries to recover a little bit. It recovers about 90% well, maybe not 90%, 80% in that 20 milliseconds. And so when the next one is evoked, it's only a little smaller. But in the presence of carbamazepine, there's less recovery, right? The inactivation gate seems to take longer to open again, so that as the sodium channel is opened more and more and more and more, the currents get smaller and smaller and smaller. This is known as use dependence, right? So one of the sort of very interesting or important things here is the size of the first pulse is exactly the same. Okay, so the carbamazepine didn't have any effect on a voltage gated sodium current when evoked in isolation, but when the channel got used over and over again, got opened over and over again, then you start to see the current get smaller and smaller. And this kind of shows the effect that it's even a bit more complicated than just use dependence, right? So this is a drug called lamotrigine that was actually developed by my PhD supervisor. And what you see here is the voltage-gated sodium current evoked with two different prepulses, one to minus 130, which gets rid of all inactivation, and one only to minus 180, which doesn't get rid of it all. And what you see is that so long as your prepulse is to minus 130, lamotrigine has no effect. But if the cell is only hyperpolarized a little bit, then lamotrigine has a significant effect, right? So it's not just use dependence, it's also something to do with this inactivation. How inactivated is the current? And so what's actually happening here is that the binding point for all of these anti-epileptics only exists when the inactivation gate is closed, right? So when the inactivation gate gets stuck into the sodium channel, the binding site exists, and the anti-epileptics can bind then. And the act of them binding essentially locks the inactivation gate in place. It sort of can't get free. It's sort of like, somebody jamming a stick into some gears, right? It's stuck it in place. And so the inactivation gate can only open once the drug dissociates from the binding site. Now, why is this so important? Because it means if a cell is very hyperpolarized or very rarely active, then the inactivation gate is never in this position. Okay, so the anti-epileptic drug has no place to bind. It can't act here. But if the cell is depolarized so that some of the inactivation gates are closed, or the cell is very active, so it's firing action potentials over and over and over again, then that binding site exists. And so the anti-epileptic can bind to those sodium channels and essentially inactivate them. So what it means is that the antiepileptic only targets cells that are hyperactive. It leaves cells alone. If the cell only fires once every second, then there's no problem. And you can see this, right? So you can take away the voltage clamp, which is kind of confusing, and um, just make a cell fire action potential. So you just patch a cell, you do a recording from a cell, you inject current. These are trains of action potentials and current clamp. And then when you apply carbamazepine, instead of getting a whole train of action potentials, you just get one or two. You wash out the drug and you go back. And same with phenytoin, same with lamotrigine. They all do the same thing. Uh, so, the sort of action is very sort of fortuitous, right? Because there are lots of drugs that we have that block voltage-gated sodium channels, and nearly all of them are completely lethal, right? So the poison of the pufferfish, tetrodotoxin, is an excellent voltage-gated sodium channel blocker. And if you eat it, well, first your mouth goes numb, and then you start to feel tingling, and then you stop being able to breathe, and then your heart stops, right? Because it blocks all sodium channels irrespective of how active they are. But the anti-epileptics only target very active cells. So, which I know this has been quite a long series of videos, but the 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 summary, right, is that epilepsy is this probably diverse collection of diseases. It really depends on how you define a disease, but it's probably this diverse collection of diseases that involve abnormal activity. But it's not, just hypersynchrony, or it's not just hyperactivity. It's something more complicated than that. We know that epilepsy is primarily a genetic disorder, but it's a polygenetic disorder. It involves inheriting dozens and dozens of genes that sum up to make your brain vulnerable to epilepsy. We talked a bit about absence epilepsy, and it involves this rhythm activity in the cortex driving. There's supposed to be more there, driving activity in the thalamus, and eventually possibly the inhibition of thalamocortical neurons to a greater or lesser extent, but certainly the rhythmic activity of TRN neurons. And finally, that anti-epileptic drugs work by locking sodium channels in the inactivated state, and in doing so, they specifically target depolarized cells or cells that are firing a lot of action potentials.